So yeah, this is joint work with Alain Paul, and there are two overlapping architecture propositions. One is archetype, the versions of the other one is the other one, and it's accessible electronically by now. I think it's open up. So I should probably explain the first words in the title about this prolate spheroidal operator, because I don't think it's a familiar notion in non-commutative terms. Okay, so it's related to this problem which was raised even, I don't know, by Claude Shannon, one of the founders of information theory, namely, to what extent functions which are confined to finite bandwidth can be also concentrated in time domain. So more completely, the problem is to find a time interval for which the signal function, you need the Fourier transform of the signal function, so a time interval for the signal function such that its Fourier transform is maximally localized on the given interval. So with this notation, I mean, take the time interval minus t and the projection onto this interval t sub t, we have the projection of the band interval, the frequency interval. The band is omega minus 2 omega, minus omega, plus omega. And what we did is to evaluate this for the Fourier transform of the signal. So the Fourier transform is in the form of displayed over there. And so what needs to be evaluated in fact is what are the eigenvalues for this compact operator with the kernel which is over there. So for the sinc function, right? This is what is sinc function. And to find, you know that its eigenvalues are between 0 and 1. Strictly, kernel which can be series, but to find these eigenvalues not so easy. So it took some time until people realized how to compute them. And the problem was solved by the group of people at Bell Labs in 1961, and Davis, Letian, Pollack, and Randall. And later, I think when he was given a prize, the von Neumann Prize, David Letian wrote that the solution seemed to him a lucky accident, namely that we found the second order differential operator that commuted with the integral operator. That was the title of the problem. I mean, it's that integral operator. So the prolate spheroidal operator, which they found was known in fact in, I don't know, 1880s or something, because it was, so that's the operator. The second order differential operator. W lambda, lambda is the same parameter the previous speaker knew. Okay. And that's a prolate spheroidal operator, and it's called like that. So it was known because it came out of the solution of this Helmholtz equation by separation of variables and using the kind of coordinates that are called Prolate spheroidal coordinates. And they are called spheroidal because they are elliptical in fact. But they are obtained by revolving an ellipse around an axis. If you revolve it around the focal axis, then it's called prolate. It's prolonged. If you revolve it around the other axis, it's called oblate. And both prolate and oblate functions, I mean, the solutions for the corresponding eigenvalues for this are useful in applications. But for us, I mean, the ones which are important are the prolate. So these coordinates, they can be written, of course, in split form. But in Cartesian form, let's see this angle in it. They look like that. Okay. So we have to using these coordinates in separation of variables, you will find the operator W lambda. Now the parameter lambda which I put is related to the two parameters. It places the two parameters t for time and omega for the bandwidth. And you can take the two parameters t and omega to be equal if you make a change of variable. So you can put them in a single parameter. Equal lambda, okay? When I mean, you can do that when you try to solve this equation, the eigenvalues. And eigenvalues for what? We are looking for bounded eigenfunctions, psi n, depending on that. Bounded on the interval minus lambda lambda. Supported on that interval, regular bounded. Because diverge towards the okay, so that was the solution found by this group of people at Bell Labs of how to compute the eigenvalues. Because instead of dealing with an integral operator, now you have a differential operator of second order. This is you know how to deal with the ODEs, second order ODE. So each eigenvalue problem is of that form. But what does it mean eigenvalues? It will be clarified a little bit later. Anyway, they found all the bounded eigenfunctions, and for that, they have very good estimate for the way in which they are close to 1 or close to 0, for instance, because you are interested in maximal concentrations, which is wanted to be near 1. You see, maximal concentration means that the signal and its Fourier transform are concentrated in the same interval. Of course, they cannot be completely concentrated because the Fourier transform is an analytic function, so you cannot have that. But you want the overlap to be as large as possible, which amounts, in terms of energy and stuff, to look at the eigenvalues that are close to 1. And they stay close to 1 for that kind of estimate, I mean, up to 2 lambda square of 5, which gave them a very good range in which this concentration was working. Okay. So, of course, they have found applications, not only for the solution of that problem, but in communication theory and optics, tomography, and other in the areas related to those are applied quite successfully, but they also appear in random matrices and quantum mechanics, maybe in some other areas. Now, the problem for us is how did they arise in non-commutative geometry? Okay. So they came up because Alencon started to think about the Riemann hypothesis in the 1990s, end of 1990s, after 1996 with the paper with Boss. Then he went to a meeting in Seattle. The anniversary 100 years from Adam Mars. Anniversary. So, at that meeting, he listened to a lot of talks related to Selberg was there too. I think it was in honor of Selberger conference. Yes. And after that, he came up first in a quadrangular note, but then in a paper which appeared in Selecta Mathematica, with now a sketch of how one could deal with the hypothesis in the spirit of non-commutative geometry. So the spirit of non-commutative geometry is that, so first of all, let's explain what one of his theorems is. I think this is theorem 4 in that paper. Yeah. You fix a set of valuations of rational numbers, but you can start with any which contains the one at infinity, the Archimedean, the place at infinity, so the Archimedean one. And we take A is from Adels. A sub S is from Adels corresponding, not the full Adels, the ring of Adels, but the one corresponding to the set of finite valuation. A sub S is just the product of the completions of Q for those places, finite places. And Q sub S, you see, they are the analog images, and then you take A, the quotient space is X sub S over the invertible Q sub S. So it's like GL1 of AS divided by GL1 of, no, not GL, matrices of one matrices of AS divided by GL1. So you make something which is non-standard in a way, because you take an additive structure and you divide by something which is only the multiplicative thing. So it's a mixture. If you can take GL1 of AS, which is the invertible A star of A, and divide by this, that would be like take the dels and the plus field thing. But what you see in this case is C sub S, I mean, this quotient, standard one, acts by multiplication on the space XS. And this representation theta of this quotient C sub S M2 of X, which can be defined in the same way like this. So, okay, so this means after you do this, you want to compute the trace of restriction of this representation. So theta of H is a scaling representation, the fact line multiplication. So you compress it with the orthogonal projection onto the subspace of L2, which is spread by functions, Schwartz function, with compact support in fact. Here you can take the Schwartz function for me. Some S is missing here. On the Schwartz space for this restricted, for this adels restricted to the finite set, such that both f of x and the Fourier transform of f as soon as the valuation of x, the total valuation of x is greater than lambda. So here I am missing some s's of the finite set. You see, you have to define what this is, and of course, you have it for each place. You just take the product of those for each place, which is in S. The Fourier transform is defined for each place, the one which I used on the other slide, and there are Fourier transforms for each place. And so the non-commutative geometry is coming from the fact that that space becomes very non-trivial if S is at least 3. The quotient is non-type 1. So it's not an ordinary space from the point of view of, I don't know, the number series. Okay, so this is how, now, what did I do here? So you need a cutoff parameter to evaluate this space. Prove that it's the operator is of trace class, restricted, compressed to that subspace. And to get an evaluation of this one, compute what it is, you need a cutoff, like for instance in the cell vector is going to need a cutoff. So that's why lambda comes in. But you also need something which is quite subtle. This is not a sum of ordinary integrals. These are principal value integrals. And so it's regularized by something. And this principal value is something which they has done. So using that kind of value integrals, okay. So you see what's involved in understanding what this formula is. First of all, looking at each terms, you see that they are just like the terms occurring in the Riemann-Bay explicit formula. So there is a well-known Riemann's evaluation formula for the number of primes less than lambda, say. But that one is in terms of some specific kind of function. Then they, I think in the 40s and it's published in 52, I think, yeah, in 52, how the extension of that formula from Riemann's formula from the function Riemann was using to any function f which is of that form, I mean, compact support and smooth on the positive, strictly positive real numbers. To take it's something like a many transform which is that. And the left hand side, so you can take any function like that. And you can evaluate the left-hand side by a sum of terms which look exactly like the sum you see here, except that not with H, but with F. Okay, so Allen's formula looked, of course, that's what is interesting about it, like similar to one in the explicit formula in number theory. However, okay, it's not an exact formula. It was, I mean, the trace was given by the estimate, and what's appearing in that formula because of the cutoff is the fact that you have to deal with this space of function restricts to the project of the space of functions which satisfy the same condition as the concentration conditions which we are using in communication theory, the bandwidth problem. Actually, this space is one of the spaces in this class of Hilbert spaces of entire functions in the branch here. So, okay, what one needs to understand is the restriction of the multiplication operator, the scaling operator, to the Sonin space. Why is it called Sonin space? It's called Sonin space because in maybe 1802, Sonin published a paper. Sonin was a Russian mathematician that published, this paper was published in French. It was at least in French, I don't know, I don't remember where, in which he gave an example of a function which satisfies this condition, but not for the Fourier transform, for the Henkel transform. But of course, the Fourier transform is like a Henkel transform, but for parameter which is not minus or something like that. So it was for Bessel functions. Sonin was studying Bessel functions. And that's why for the Henkel transform he needed, because otherwise you could think that these kind of spaces are empty. He showed that there are, I mean, one showed that they are non-empty. Then the branch gave more examples why they are non-empty. I mean, we proved the theorem saying. Anyway.
Sorry. If you go back one slide, so maybe you said that, but there was a inequality that was in the wrong direction, or what? If you go back one slide,
yeah.
So they should vanish for. So you have the opposite, is that right? Because you project onto the interval lambda.
Oh, what? I project on the x for x.
Then you cannot vanish.
Yeah, vanish for x less than lambda.
Okay. Yeah. Because this will never be possible because of what you have.
Sure. No, but one restriction at the same space very restricted. Project onto the same, so yeah, it was a type.
Yeah, okay. So this is possible, right? So you project onto this interval minus lambda.
The projection onto the interval minus lambda should be 0. So that's the interval where you wanted the concentration for something which amounts to. Okay, that's a Sonin space. I mean, that's a relation with the Prolate operator. But it's true that they are complementary in a way, but they were looking for concentration, but it's needed here. But yeah, what is really here is here is missing also.
No, this is okay.
Where lambda, I lost it. Lambda less sine. P lambda, yes. P lambda is 0. Okay, so what missing is the lambda. All right. So that's a Prolate wave operator. Now, I mentioned something about the eigenvalues before of the Prolate operator restricted to the interval minus lambda lambda. I said that that's how they found model basis for the interval which allowed them to find the eigenvalues lambda, 0 lambda, 1 lambda, and for the integral. Okay, but now what is interesting from this point of view is the eigenvalues in general. So what Alain did from the beginning, well, of course, he put it into the context of self-adjoint operator. So you have the ordinary differential equation, given that by the Prolate equal to 0, or if you want eigenvalues, it's equal to mu times psi. It has two finite singular regular points, and the infinite ones are irregular singular points. But you can still find the formal solution series by the usual theory. And there is in many places you can find it, but there is a very good paper by Ramis and collaborators in which they analyze the solutions and the possible eigenvalues from the point of view of ODE. Now, what Alain did was took this operator with a chord, the Schwartz function from the real line, not just minus lambda lambda. And well, it's a plausible operator. It's obviously symmetric. It's invariant under the parity x goes to minus x. And you can also check that it commutes with the Fourier transform. So that's also easy. Check. So these two guys, take the Fourier transform. You see that it will commute with it. The other one is a harmonic oscillator, which of course is invariant under the Fourier transform. So these are obvious features which are inherited, of course, by the closure and by the maximal domain. So what is a maximal domain? Well, if you take it with this chord and you want to be commuting with the projections P lambda and P lambda hat, which means P lambda and the Fourier transform, then there is only one unique self-adjoint extension, which the domain is determined by 6 parameters. But two of them have to match. And because of the matching agreement with 4 parameters, so we have the efficiency indices 4 and 4 because of the counting. And there is a unique self-adjoint extension of W mean, which terminate with P lambda and the Fourier transform. That was an indicated proof in his course in 1988. Okay. The boundary condition to translate it into, I mean, the domain of this self-adjoint extension, if you want to understand it in terms of boundary condition, it's best to use Sturm-Liouville theory. And you can certainly do that. And then the boundary condition for this self-adjoint extension can be written explicitly in terms of what happens plus lambda minus lambda equals to the points. That's a singular point. But for the irregular singular points, there is a difference between the even and odd functions. So that's a domain. It splits into an even and odd part function satisfying this condition. Now, connect with what I said before that the large people function. For the finite interval minus lambda lambda, the conditions are the same as saying that the limit towards lambda and minus lambda is finite. So it's indeed what they were counting for the finite interval, because they look for the bounded functions. Remember that the other possibility I mentioned here implicitly, there is a logarithmic singularity for one of the solutions. One of them, if you look at solutions of differential equations, one of them would be maybe like the log of x near the finite singularities, the other ones without log. Okay, so in terms of Hermann Weyck's classification of real problems, this is a really certain non-oscillatory case that plus or minus lambda, and oscillatory at plus and minus infinity. Oscillatory means that it do oscillate a lot. For the finite interval, I mean close to the finite interval, they are fine. But otherwise, the solutions have infinitely many zeros going to infinity. Okay, so what you can get from the Sturm-Liouville theory is that the spectrum is unbounded on both sides. And it's unbounded on both sides because of this oscillatory behavior at the infinite endpoint. So WSA, this self-adjoint extension, must have negative eigenvalues, okay? Which were not seen before. They were looking on the finite interval, there were only positive eigenvalues. Okay, now, since the positive eigenvalues which were found are not really interesting from this point of view, one should really concentrate on looking at the restriction to the complement of the finite interval. So what it is, W splits into, as I said, into restriction W prime splits into even functions and odd functions. Each of them acting on a subspace because they are either even or odd. You can just take the positive part from lambda to infinity. And the restriction to this interval comes under standard Sturm-Liouville theory, because otherwise a Sturm-Liouville theory deals with 2 endpoints, not with 4 endpoints normally. Okay. So what we see from that analysis, the spectrum of W prime is simple and unbounded on either side. It inherits positive eigenvalues not from the Prolate functions. Prolate functions themselves, we want to show the eigenfunctions for the finite interval. I don't know if I said, but they are called Prolate spheroidal wave functions. I mean, the solutions for the restriction of the Prolate spheroidal operator to the finite interval. So, if you take their Fourier transforms, they remain eigenvalues, the same eigenvalues, right? Because the operator is invariant under the Fourier transform. So, even if you restrict to the complement of that finite interval, you still get the positive eigenvalues, but in addition, you get negative eigenvalues. Okay. So, the restriction to W prime is also good because it gets rid of of doubling the spectrum, the positive part, I mean, the eigenvalues, because if you keep the full operator, you will have eigenvalues coming from functions concentrated with support and minus lambda lambda, and their Fourier transform, which is not concentrated. Okay, so, all right, the spectra of the positive and negative are joined. Now, I call these other new eigenfunctions, which correspond to negative eigenvalues, I call them here extra prolates, because they're not the ordinary prolate. Now, how to find them? The key lemma, which uses, as I said, the analysis in Ramis and collaborators, is that, so there are solutions, formal solutions, which can write, because we are dealing with ODE. Then they show that they are Borel summable, but moreover, in Ramis, they show that there is a relation between the coefficients of the corresponding series expansion, between the relation between the coefficients of the series around lambda or minus lambda and around plus and minus infinity. Using this, we prove that calling the psi mu once which at infinity. Remember, there were boundary conditions. We showed you that one of the functions, one which behaves like sine x over x, like a sin function like that. So it's even. One of the function at infinity should behave like that. The other one, for the mod one, should behave like the other one. So what you see is that the one which behaves like sine over x has the Borel Fourier transform, is the Borel Fourier transform of the unique even reflective mode solution, which is 0 at the finite singularity. And for x greater than lambda, coincides with the regular solution around lambda. You can always write the series representing solutions for a while around lambda. Now, as a corollary, you see that if mu is a negative eigenvalue, so by the way, I should say that if mu is an eigenvalue, then this Borel summability becomes convergent. It's summable. If mu is a negative eigenvalue, then the power series converges, and the solution is the same in this way belongs automatically to the Sonin space by construction. So you take it, the solution which is 0 minus lambda, okay? And it copies something from the coefficient of this solution which is around lambda. Okay, so by construction, they are 0 where they have to be, and the Fourier transform is also 0 because of this, the way you found it. It's a Fourier transform of a solution which was 0 minus lambda lambda. Okay, so which means that that's how we can find eigenfunctions for negative eigenvalues. All right. So we remove the duplication of eigenvalues, restricted to the complement of the integral. Now we want to evaluate the distribution of the negative eigenvalues. So first, for a semi-classical approximation, you take a related Hamiltonian look like this. One is nice. And so it's not exactly double prime, it's up to multiplying by this 4 and 5 and adding something. So in this picture, d lambda, the Sonin space would correspond to this region. And the eigenvalue counted in these regions are again by areas or volumes like in the previous talk, and this is what we get. They are given by this integral. Okay, so this can be evaluated by elliptic integrals, and you get the semi-classical counting formula for the eigenvalues, negative eigenvalues, which begins to look like first term, like the Riemann's formula for the zeros, distribution of the critical zeros, or the non-trivial zeros. Okay, now where is now you see that here we are dealing, I put an E squared because we are dealing with second order operators, so you have to take the order into account to get exactly, that's why the square appears, that's why this 4 appears here in front of the counting function. You account for, there was a 4 someplace here, and there was a square. So to get closer to the distribution for the zeta function, you further restrict to this complement of the finite interval, but you also have to take some square roots, okay? Now, taking square roots means that you want to view W like a Laplacian somehow. But it's a Laplacian, it would be a Laplacian not for the Riemann, ordinary Riemann metric, but for a Lorentzian metric, because it has also negative eigenvalues. So, it's not a standard construction to obtain square root. And in fact, you obtain not just one or two square roots, you obtain a whole family of square roots by what's called Darboux factorization. Method which is used under the name Darboux factorization. So I looked at the paper of Darboux and he gives credit to some other, which I forgot, another French mathematician for the idea. He was dealing with a single equation, not with a second order equation. And the factorization is that you want to somehow split it into one operator times another operator. In our case, we want the operator to be something which involves the derivatives, okay, which is nabla, plus multiplication by a function. And it turns out that what we need to get the equality that W is indeed the product of these two things, we need for W to satisfy this equation. It's a Riccati equation. And it's well known how to deal with the Riccati equation. We look for solutions of a certain form, nabla, the derivative divided by them. The problem is that, as I said, and you want this to be a solution of the ordinary equation W equals 0. W equals 0. But they have zeros, those solutions, because of the oscillatory behaviors towards infinity. They have infinitely many zeros. So what you have to take two solutions, linearly independent solutions, and put a complex parameter which is outside the real line. Okay, and then if you do that, then you get all possible solutions of this Riccati equation. So the parameter varies into the complex plane with a real line removed, and this is the holomorphism. And this gives you the Dirac square roots. They are called Dirac because Dirac took the square root. Second order operator. It's similar in the similar spirit, but this is the family of square root. It's a whole family, so it's now parameterized by a complex parameter outside the real line. So for each such solution of the Riccati corresponding to you get an operator. This is the domain of the operator, so it acts on two copies, on the direct sum of two copies of the Hilbert space I'm working with. It's equal to lambda plus infinity. But it's not completely okay. So what you would like from Darboux's factorization is to get two isospectral operators, this and this. They are isospectral, but they are not necessarily, the second one is only quasi-Hermitian. I mean, you cannot make it to be self-adjoint like this one. Okay? For the same metric. You need to modify the metric by a positive operator, and that's called quasi-Hermitian instead of Hermitian or self-adjoint. Okay? That's the terminology of I think so that's a square root. It's a square root in the sense that if you take the square of this operator, its spectrum will be exactly made of the spectrum of this reproduced again here. Okay, the same spectrum. So the spectrum now, that's a square. So the spectrum of E is plus minus square root of mu. So you have imaginary and real eigenvalues. Okay. Now, better than semi-classical counting can be done again from Sturm-Liouville theory, but based on, this is the first counting formula was done by Hermann Weil for some Sturm-Liouville. But there were all sorts of extensions, and anyway, that's how it will indicate how you can count the number of eigenvalues with positive imaginary part less than given E, and you find this formula, which is very similar now with the Riemann estimate. So now it's better than the semi-classical one because it sees this no. Okay, so this can be done by, you have to pass to the Schrödinger form from the one which I use for the operator, which is again standard in Schrödinger view transformation. And in the inverse of this is just simple. You find the unitary operator which conjugates the Prolate Dirac operator with a given potential. Yeah? And for this, there are classical formulas. One of them is which we use is due to Henri, the student of Fishmash, and extended the Fishmash counting formula to a larger class of Schrödinger operator, not large enough to cover ours, but it was then extended by others to cover the case, the potential, details, and 0 and infinity, so now you are on the interval 0 and infinity. In a way which allows you to apply Haywood's type of formula. So Haywood has formulas for both, counting formulas for both positive and negative eigenvectors. Okay, so using the ones for the, in our case, the negative eigenvalues, which is actually Haywood's for positive, because the non-homogeneous equation in the one side, the left side. The eigenvalues become from minus plus because he moved them back to the equal side. Anyway, using here the dynamics the integral eigenvalues, which can be done again by elliptic integrals, but there are more elliptic ones, which is elliptic here. I didn't put it in. We didn't even put the calculations in brief papers, which I mentioned earlier. So, just to get an idea, if you want to compare the two, of course, they are not like exactly. So, comparing the imaginary parts of the negative eigenvalues of this scale by 2D, D is one of these is, and the ones of the zeta function, you see that they are almost the same, not quite the same. And in fact, it works for the positive eigenvalues for it. I mean, they are like the trivial zeros, because for the square, they became like that, asymptotically. I mean, the eigenvalues. So they behave exactly like the zeros of the zeta function, square, the trivial zeros. Well, but with a shift of 1/2, the shift of 1/2, which is the same to match to the theorem in Dirac, which is a single line, to match the shift for the trivial zero. Okay, in particular, this implies that if there are other positive eigenvalues which we didn't see coming from the complement of the interval, we can always be finitely many, but we don't think that there are any others. But anyway, we are not going to prove the Riemann hypothesis just by computing eigenvalues and saying that, oh, they are getting very close. Because neither for the zeta function, nor for this operator, you cannot do exact computation. So, I mean, you can only use machinery to go as far as you want. So that's not the way to handle the problem. I'll make two closing remarks related to this. One of them, symmetrically, they are due to André Bey's photos and they're related to what by André Bey. One is that if you look at this operator, it's made of pieces which come from the universal enveloping algebra of SL2. This is the standard basis of SL2. W lambda is exactly expressed in terms of the standard basis, but as an abstract operator in universal enveloping algebra. Now, if you you take so I call it script W lambda. This is not the W lambda which I mentioned before, but that one can be recovered from this one if you move it by the differential of the J representation of the metaplectic representation. SL2 has a representation of its double cover, which are called SL2 tilde, which is called the metaplectic representation, which exists not just for SL2R, but SL2 over any field, for the local field. And if you take the differential in the case of SL2R, you get exactly the Prolate Dirac. So that's a coincidence which is remarkable. The other one is that, remember that I mentioned the Riemann-Bay formula, the Riemann-Bay formula in this form. If you call this left-hand side, this one, yeah, you call it by T over it, it's a functional, which is called a Bay functional because he looked at it. And he showed that it's a sum of local terms. I mentioned before. In a paper by Kona and Consani, 21, they showed that if you take a function which is local, I mean, we support between 1 over square root of 2 to square root of 2. This is like minus lambda lambda, but in the multiplicative version. So 1 over lambda lambda, which has this thing 0. Then, for the Bay, this is the Bay quadratic form now. For the Bay quadratic form, we found this inequality. Now, what was known from Yoshida was that this left-hand side is positive for functions with this support. If you could prove it for functions with any support, then André Weil showed that this is equivalent to the Riemann hypothesis. Okay. So, what Kohn and Consani did was to show that there is a good reason why this is positive. It's because it's a trace of something which is a positive operator. Right? R1 is the projection onto the Sonin space -1, 1. So, what needs to be developed is a sort of extension of the Prolate spheroidal machine to the semi-local case, because that's what they use to get this inequality. At the Archimedean place, it's enough to get an inequality like that at the Archimedean place, but for functions with arbitrary support. Why? Because you have to let the other primes come in and correct the formula for the trace. So the correction should come from adding more and more primes. But the good thing about this approach, also by Bay, to deal with the explicit formula and number theory, is that you can restrict to functions with complex support. However, the support has to be as large as you want. This is how the primes get it. Okay. We don't know that. This needs to